All right, it's my pleasure to introduce Abigail Ward from MIT, who will talk to us about symplectomorphisms mirror to birational transformations of P2.
Well, thanks very much for the invitation. So everything I'm going to talk about is joined with Elsa Keating. And as I said, I'll try to emphasize more of sort of the group theoretic stuff here, like more of the algebraic geometry side than the symplectic side. But it's a slide talk now. I'm regretting giving a slide talk. But it always goes better with the slide talk because there's sort of a lot of background. I'll just start with that, I guess. Yeah. And I also kind of did a Beamer style. I think this. Okay, so the background and notation. So the main thing object that you guys should know about that maybe you don't is the concept of a Luinga pair, some people call them, or a log-Calabi-Yau surface with maximum degenerate boundary. But what this means is just some smooth complex surface Y and some anti-canonical divisor within Y, which takes the form of like a cycle of P1s. So the simplest possible example of these kind of objects are just toric surfaces with their toric boundary divisor. So if you like P2 with its like 3 lines at infinity. Some more notation. So when I talk about the automorphism of such an object like a Y comma D, so that's a phi in the automorphism of Y, and I remember that phi fixes the divisor G point Y. So sort of at infinity, it acts as the identity. And then moreover, so this just notation for the top, a morphism of these objects is going to be some bihole, like some map Y1 to Y2. So like a regular morphism. And I'm going to demand that it sends D1 to D2, but not necessarily, these don't necessarily have to be biholomorphisms the way I've set it up here. Final thing. Oh, wait, now, great. And the important piece of background to know about this from algebraic geometry is that if you look at the interior of one of these log-Calabi-Yau surfaces, so you look at one of these Y and you subtract U to get something U, then that U embeds into some log-Calabi-Yau surface as in the following way. So you take some toric surface, and then you know that you have a copy of C star squared, or if you like GM squared, sitting inside of the toric surface as the complement of the toric boundary. And if you start blowing up interior points on the toric boundary divisor, and you take the proper transform of the boundary divisor, then you get one of these log-Calabi-Yau surfaces, and then you can look at the interior of that and you get back the original U. So sorry, so that was, let me like now do something which is probably a terrible idea, which is like kind of draw what I mean by this. So if you look at like, if you let this be my picture of P1, and I can say, okay, well, like if I start blowing up, so these are going to be like exceptional curves. Then so this would be like maybe like blow up. I'm going to push this up too. Like the blow up at two blow ups. Sorry, P2, not P1. And then minus this triangle of lines. So I look at subtract the complement. Or I look at the complement of the triangle of lines there. So this is like a new log-Calabi-Yau surface, and in the interior, I start with my original C star squared, and now I've sort of added on this like chain of P1s. So so the interior is not super affine if I do enough blow-ups. And I know that I can obtain all log-Calabi-Yau interiors by some method like that by work of gross happening Kiel. So that's the sort of algebra geometric background. I promise I'll get to what this has to do with birational transformations too. Now the background on mirror symmetry. So I know no one here is really a mirror symmetrist, so let me just go through this quickly. So in 2021, Paul Hacking and Elsa Keating proved homological mirror symmetry for these objects. So they showed to one of these log-Calabi-Yau pairs YD, they can associate some symplectic space M. So M here is a symplectic manifold with a superpotential W, so just a holomorphic function W from M to C, such that if you look at the Fukaya-Seidel category of that Landau-Ginzburg model, the derived Fukaya-Seidel category, which is on the right-hand side here, is quasi-isomorphic to the derived category of your original log-Calabi-Yau surface Y. So what you want to think about there is let me again just sort of use the board to like write down the background stuff. So I have like this derived category of Y, isomorphic for this like derived Buchanan-Seidel category MW. And like if you don't really think about homological asymmetry, that's not really a problem. You just want to think that this has like coherent sheaves on Y, and then this has objects. So the objects are coherent sheaves on Y, and the objects of this are equal to Lagrangians in M, obeying certain boundary conditions. But that's the like A to B resymmetry there. And then in 2022,
Sorry, I
Yeah.
missed something, maybe
Yeah.
anything, but in that equivalence category there,
yeah.
how does D figure?
So that's a good question. So if you just look at right, so it's a let me back up and say why you need the D. So if you don't put this D here, then this you could still form the category of coherent sheaves, but
Yeah.
the Buchanan-Seidel category is like some A infinity category. So you really want to consider this category up to this like derived equivalence, so that you can get like an honest triangulated category out of it. And what this is going to mean is that like your Hom complexes here. So I'm trying to figure out the best way to answer this question. All of the equivalences you're going to see, for example, once you match up like morphism spaces between the two categories, are going to like just exist sort of on the derived level, or they're going to like exist as quasi equivalences. I don't think I'm answering the question very well. So
But for example, a version of the question could be that does the equivalence depend on D at all?
does the equivalence depend on?
The D doesn't appear, this divisor of D doesn't appear on the left hand side.
Oh.
It's not explicitly, so that's.
Like this GB here.
No. Okay.
Sorry.
Yeah.
Yeah, okay, great question. I was being, that's a very good question. That's a much easier question to answer because I don't have to like try to figure out what to say homological book. Yeah. So the divisor D, in this specific equivalence here, yeah, the D doesn't show up, but you also have equivalences like this. So you also have like, I didn't put this on, but you also you have du, so u is equal to y minus p.
Yeah.
So this thing is probably equivalent to the Rappenheim category of this MW. So if you take these boundary conditions, but then you compute Homs differently in your Buchanan-Seidel category. Like if you start so-called wrapping at infinity, then you get an isomorphism of the derived category of the interior, and then the final piece of like this triangle is like you have like the derived category of your T is isomorphic to like your Buchanan category of your fiber of your superpotential.
Maybe my question is silly, and you already answered it at the beginning. Say that, as I think you put in your slide, the simplex manifold M, W itself depends on D. It doesn't just depend on Y.
So M depends only on the interior U minus D. And
So
then,
it depends on D. So to speak.
Yes,
So,
yeah,
so,
yeah.
I mean,
yeah, sorry. And then
I
your
see.
superpotential W depends on D.
I see.
That's what,
So asking whether that equivalence depends on these pointers, because the right hand side is varies in D.
yeah.
Okay, well, sorry.
Yeah.
Mhm.
But indeed, I could have chosen, it's a good question, and watch like this, like I could have chosen a different D inside of Y.
Yes,
Yeah, and then I could have had a different presentation of like some here.
Right.
But then you would actually see in the end that they should be giving you the same symplectic manifold.
you're right.
Yeah,
uh-huh.
yeah, exactly. Okay, yeah, sorry, that was a really great question. Thank you. I'm sorry, I didn't understand it at first.
Sorry, can I have a
Yeah.
much less, probably less good question, but what?
There will be a ranking. Right? I will keep here.
What are the morphisms on the right side?
That's a great question too. I think the questions are tied. The morphisms on the right hand side, let me now move on my other. If I write Tom, let me answer this sort of cheekily. If I write Tom, Fukaya MW of like L prime, this is as a chain complex, this is equal to like C times the chain complex generated by intersection points of L and L prime. So in general, the way you set up these Lagrangians is they intersect in finite unique points, and those intersections generate the Hom complexes. Now you're going to ask me, well, how do I like compose morphisms? And then that would be the next step of the story. So you want to count holomorphic triangles or whatever. But I'm not actually going to use any of that for this talk. So okay, great questions. Okay, so just the last part of this HMS background is in 2022, Paul and Elsa enhanced this correspondence to actually get a map from the automorphism group of this YD. So recall that's the kind of thing that acts trivially on the boundary divisor infinity to the group of compactly supported symplectomorphisms of M, compatibly with the HMS, meaning like if you look at the induced autoequivalences of these derived categories, they match up, like you have some commuting triangle of autoequivalences like so. So a symplectomorphism, which this is a compactly supported symplectomorphism, a compactly supported symplectomorphism will act on the Fukaya category, will give you an autoequivalence of the Fukaya category. And they identified which autoequivalences of the Fukaya category can be identified, like which geometric autoequivalences of the Fukaya category can be identified with these like so-called geometric autoequivalences of like this derived category coming from an honest like automorphism. So that was the story at I guess the beginning of this year.
So saying this kind of this equivalence is kind of equivalent with respect to
Yeah, exactly.
automorphism with the pair.
Yeah, exactly. Yeah. Well, once you match up the automorphism. Yeah.
How much bigger? Well, yeah, actually, how much bigger is the right from the left? Or I mean, like the two sides of this thing, or is there?
Right. So this side is finite. It's a good question. I think they don't know.
Okay.
This side here, I mean, a priori, this is much bigger, but if you start modding out by compactly supported Hamiltonian isotopy, which is what you want to do, I think this is conjecturally an equivalence, but I don't think that, or you can enhance this to basically be conjecturally an equivalence.
Okay.
Yeah.
Cool.
Okay. So that's their stuff. Okay. Now more, that's all the background log code-based services. And now the background and notation part 2. So this is the notation on the group that I'm actually going to be considering. So it's this group Bir P2, omega. And what these are is birational transformations of P2, which preserves some mirror-morphic volume form on P2. So it preserves this volume form, which you would write d log x, what d log y on C star squared sitting inside of P2. And that's the mirror-morphic volume form with simple poles along the toric boundary divisors. One group here, or one note here is that I started with some toric variety, this P2 with its triangle of lines, but I could really have chosen any toric variety with any toric boundary divisor. This is just like the statement that any two toric varieties are birational. As soon as you fix the embedding of this GM squared inside of like the toric variety, then you have an honest equality, right? It's not even like abstract isomorphism of groups, like you could honestly have just written like beer like y bar comma d bar, or sorry, y bar comma omega. Like this is also going to be the mirror-morphic volume form in any toric variety that has simple poles along the toric boundary divisors. And then in 2013, Jérôme Blanc showed that this group beer P2 omega is generated by three sorts of elements. So the first two just act on like the algebraic torus sitting inside of your toric variety. So this FL2Z and GM squared. So that's the fact, like FL2Z just acts by like, let me actually like get it right. So like SL2Z sends like X, Y maps to something like X to the A, Y to the B, X to the C, Y to the D. That would be like A, B, C, D. I don't know if I've chosen anything, it might be that or it's but it acts. So this preserves the torus sitting inside of the log project, or like sitting inside of P2, and then this GM squared just acts by scaling, so that's X, Y goes to lambda 1x lambda 2x. And then this E is like this cluster transformation. So this E does not preserve the algebraic torus. And let me actually write that big because I'm going to need it. So E of X, Y is equal to X, X1, well, sorry, Y1 plus X inverse. So that's your presentation of your group. And then for the rest of this talk, I'm just going to focus on the subgroup sitting inside it. So if you look at the subgroup just generated by these like discrete guys, so this SL2Z action plus this E. So this is what I'm going to call this. Yeah.
Can I ask a question?
Yeah.
So is there a way to say this more, how do you say, intrinsically? So it looks like you picked a cluster transformation, but presumably that together with the SL2Z will generate a bunch of them. So is there a way to say more intrinsically what that bunch is as opposed to, oh, here's the particular perhaps nicer than other cluster transformation. I mean, why this one and not another one is I guess part of it.
So the reason that I chose this one, not the other one, is because I can it's going to be like at the end of the day, I'm going to produce some symplectomorphisms like near to these guys, and this is the one that has like, I would say, the nicest symplectomorphism as its representative. There's probably a good answer to that question on the algebraic geometry side as well, but I don't know it. It's what I want to say here. Yeah, but I mean, you're indeed right that like I could have chosen a lot of different cluster transformations here, and I don't have a good answer on the. In fact, Jeremy, like in his paper, he uses a different generator here, so I don't know what's the most natural choice, but you do need some.
I wasn't asking necessarily about what the best choice is. It's a question of what is this point of all choices. I mean, does that have some intrinsic description?
Yeah, I don't know the right answer to that. Yeah. But yeah. Yeah. Hopefully you'll see why this is the right choice for our purposes. But yeah, so then I'm going to focus my attention on this discrete subgroup, this sphere sub E sitting inside of this whole group of birational transformations. But no, we haven't lost that much information because I've just kind of thrown out this like continuous, like this part here. So this is just some discrete subgroup of the isomorphism on the connected components. I can also talk a little about the whole group in the answer. This is my sphere sub E. Okay. And now let me connect these volume preserving to sphere sub E to my log Abigail services with their torus models on the next slide. So if I act, okay, yeah, so I'm just gonna, I already said I'm gonna map this group sphere E to this simp mod Hamiltonian basis for Hamiltonian. Okay, so let me now connect the two stories I've said so far. So if I think about if I say I have two torus surfaces and I have a phi mapping between them and say that I know it's in this group sphere sub E. And so that actually tells me that I hit some sort of birational morphism of log Abigail surfaces, meaning like where this thing is defined is going to send E1 birationally to D2. Probably I don't want to say that right. P1 is going to send X1 to X2, and then where it's defined is going to send D1 to D2. If I want to resolve, so I know like from like resolution of like surface singularities, I can blow up some points in the indeterminacy locus of phi and its inverse, P1 and its inverse, to get an honest bihomorphism, right? So if it's indeterminate on some point, I just blow up that point, and I can do this finitely many times to get an honest biholomorphism. And so this is one of these morphisms of log copy surface at a time, right? So it sends D1 to D2. So for example, like if I look at this E here, inverse So I would note that if I was trying to if I applied this EXY to like say P1 times P1, then I would have an indeterminacy at like -1, 0, right? Because this would be 0 and that would be 0 as well. But if I blow up that point, -1, 0, then I get an honest rational morphism. And similarly, if I blow up the inverse, I can get a nice well-defined map like so. The problem is now comes like, okay, well, what if I try to compose two guys? So let's say I have, say I've done this again. So I have another birational map. So again, on my like this surface 2, x2, d2. Okay, I can blow up in the indiscriminate locus of this d2 to get a new set of surfaces like so. But I can't yet go from y1 to y3 yet. I have to blow up sort of again to get an honest like chain of morphisms. So the idea here is that like if you want to think about some set of spaces where the full birational transformation group actually you need to sort of allow all blowups. And 2 points here. So if I have how I've constructed these surfaces like that is manifested like a Lewinga pair or one of these log Poincare surfaces with an explicit toric model. Because I told you an explicit toric model is like I take a toric variety and I blow up points on the interior points of the divisors. And I guess I didn't say this on the slide, but I'll say it in words like, you know, the indeterminacy locus of these guys is always going to live within the divisors because you know that it preserves the volume form. So you get manifestly, you get some sort of power of Lewinga pairs of explicit toric models. And moreover, if your phi is in this distinguished subgroup, then each pair is distinguished among its complex deformations. I haven't told you what that means yet, but you should imagine that like I've gotten rid of the moduli in this group by taking the sphere sub E group, and so I've also I can imagine I've kind of gotten rid of the moduli in my log Poincare services, and I didn't make a big point of this because I wasn't going to do the rest of I didn't make a big point of this, but the Hacking-Keating mirror symmetry work is for these log Poincare surfaces with their distinguished complex structures. So if I need to have a mirror symmetry story, at least using the Hacking-Keating work, I want to have all of these log Poincare surfaces like so actually have their distinguished complex structures, and that's what I'm guaranteed by working within this distinguished subgroup. Okay, so questions on this so far? I guess I haven't really. Okay. So let me get to the statement of the theorem, and I'm gonna I'll tell you what everything that's happening in this theorem. But so the theorem that we prove is that there exists some sort of non-finite type Weinstein 4 manifold in the universal, so that so first of all of your mirrors, so all of your MCs that you constructed, and like this mirror correspondence here, this M universal is like some Weinstein 4 manifold, which contains all of those mirrors as a subdomain. And furthermore, if you think about, well, furthermore, there's some injected map from this group of birational transformorphisms, this B sub E, to the symplectomorphism group of that M universal. Mod compactly supported Hamiltonian isotopy, which we should think of as acting as like equivalences. And moreover, like this correspondence knows about this correspondence knows about the mirror symmetry in the sense that like if I have one of these maps, a biholomorphism of these log Poincare interiors, then in particular this phi, if I think about it, like in coordinates, well, that gives me some birational transformation of P2 preserving the volume form. And so that gives me one of these symplectum. So that gives me an element of this symplectomorphism in the universal group. But then by restricting the subdomains, I actually get a symplectomorphism of the Weinstein subdomains. And moreover, like you have some commuting diagram like this. So this correspondence here is enhancement of the Hacking-Keating correspondence, because now instead of just thinking about sort of the automorphism groups of the Y comma D, which we know those are all finite groups, this is some very infinite group, and it acts properly on this space in the universal, and in sort of a nice enough way that you can actually get some geometric information out of it. So that's a theorem. Let me pause. for questions. I also know this slide is like very small, based on this small screen. So I'm also happy to like, let me just like rewrite on one of these things now.
So the automorphism groups of each of these Lagrange pairs,
Yeah.
they're finite, so that you get like finite subgroups of SL2.
We'll find a subgroup to this SL2
And
comma E thing.
okay.
Yeah. So they're not really serious.
Can I ask a question about
Yeah.
that? So, I'm sorry, I missed something you first said. So you're modeling out by the Hamiltonian.
Yeah.
Is that because otherwise the math would not be injected, but also because otherwise the math would not be defined? Is that because of that lifting thing you have to know? Or not?
It's a good question. It's an argument between me and Elsa. I think the safest thing is to say that the map might not be well defined.
But that was because of that diagram you had with lifting, differently lifting too.
No, it's actually just kind of a technical problem of like how well can you define a symplectomorphism on
M.
Yeah, sorry, let me say, so yeah, so this compactness of curves symplectomorphism or Hamiltonian is the thing. So let me actually write this. So yeah, so the map is something like this here. E P2 omega maps to sim M unit mod and sub C M unit. So these elements, okay, now I'm over the thing of the screen, but the elements of this cam C M unit. So those, if you like those can be
Actually, I really like that what he said was not right. So but the point is that when you lift, so you have a birational map to lift it to an actual honest law, you're making a choice there, right? Is that you can do it, but you can do it in more ways than
yes,
one.
exactly.
So that's accounting for this. Is that
yes
because you want to kill that choice in some sense.
Yeah, exactly. So you want to just consider sort of all possible powers.
And that forces you to take that forward.
Yeah. Well, so the quotient here has very little to do with that actually. So the instead passing this in universal is what's sort of the analog of like killing that choice. So I could have, let me actually pass to
I mean, maybe I don't want to slow you down, so
well, let me come back to that.
Okay.
Yeah. Yeah, it's a good question. So okay, so now let me see. So okay, yeah. So we want to construct this immunov, and so I hope it'll be more clear once I actually do it. So to get this immunov, I'm going to write down two directed systems. So let me kind of go through this a little bit. So so this left-hand side of the slide here is sort of my algebraic geometry log or directed systems. So here, this is so here I'm going to consider the set of all Lagrange pairs with explicit toric models, and they're going to form a directed system under blow up, and that's what we saw previously with these like towers. So if I can write down one log Poibier surface as the blow up of another one, then it's going to live above the first one in my like tower of log Poibier surfaces. So that's fairly natural, and I can record this with like some sort of combinatorics. Because I knew that I was getting all of these from like blowing up interior points on boundary divisors of some toric surfaces, and I know toric surfaces I can record by like just their fans, right? Like their fans living inside of R2. And now I'm going to draw these little so-called like enhanced fans, which means I just take like some fan living inside of R2, and then I decorate the rays depending on how many blows I've done. So this here, so here I've taken, this is an example, which maybe you guys can see, but you can't. So this is like the fan for P1 times P1. And now this would be if I've blown up like twice on sort of opposing components of the toric boundary divisor, and then 2 times on a, like it would be like if I've done like something like this. And the point is that I can use these little diagrams to actually construct my mirrors. So this is, I won't spend too long on this because you guys are again, not symplectic geometries, but I'm going to construct these as just kind of do the whole thing. So I'm going to construct these as Lagrangian almost stroke vibrations over bases with integral affine structures with singularities. So from my enhanced fan, I can read off a base, this space with an integral affine with space with singularities. So that's just some two-dimensional space where away from isolated points, I have some lattice sitting inside of the tangent bundle. And then what I can do is I can form some symplectic form manifold over that space away from the singular points in the base. It's just going to be like T star base mod lattice, and then over the singular points in the base, I'm going to fill in with some pinch tori. So topologically, it's just what you would expect to see with like a leftward vibration. But here, everything is now in the Lagrangian setting. But so the point is I get some form manifolds, and these form manifolds have some description in terms of these almost stroke vibrations. And this description is also compatible with the ordering that I put on these Winger pairs. So if I have, I construct these bases using these enhanced fans, and then I note that my ordering on my log Fabio services is kind of reflecting these fans. So if, okay, so there's a typo there, but if one of my log Fabio services lives above another in one of these towers, then the fan of that upper one kind of includes the fan of the lower one. And then as form manifolds, like over here on the mirror side, that means that the form manifold mirror to the bottom one includes into the form manifold mirror to the top one as like an integral affine space, or sorry, as a Lagrangian force vibration. And so I can construct a form manifold. So now I'm in like the smooth mode. What I can do is I can just construct a form manifold by just taking exhaustion by all of these mirrors to my MC. So now the nice thing to do is show the picture. So the base, so this thing fibers over this base, this B unit. And so this is some integral affine space where what I've done is I've put a singular guy at all points of like Z2 minus 0. And I have prescribed, I mean, okay, if you know about these integral affine spaces, you can read this picture. If not, this whole part of the talk is like hopeless. So let me not spend too much time on it. But this you should think about as sort of the universal base for exact almost stroke vibrations in 2 dimensions. And this is my B unit, and then I build my M unit by taking. So let me actually write this on the board.
It's like these maps not depending on the blow up. Again, this kind of gets changed into like being able to extend into bigger domains.
Exactly. So the point is that I had some choice in like how I resolve the singularities.
Yeah.
But on the right hand side, like all of the choices are going to embed into this in universal. Or sorry, like all of the corresponding choices on the symplectic side are going to embed into this in universal. So this is like equal to some let's say like partial compactification of this like T star a unit on where the unit where the compactification, like the partial compactification by which I mean like if I have a singular fiber like this, if I have a singularity, this is a piece of the base unit, I have like some sort of pinch tori here. And then I have a family of smooth tori. So this is B unit. B unit not equal to B unit singularities. So I have a Lagrangian torus vibration over that base, and then I fill it in with these like pinch tori. So this is my B unit, and then unit just lives above it. And then now, let's see. So I think I actually sort of went too quickly because I was too happy to skip this symplectic geometry. So now let me pause for more questions on this.
Because you didn't talk very much about the M MWs, the
yeah,
mirrors of
Yeah.
like how
Yeah,
does it kind of how do
yeah.
they like sit in here?
Yeah, so right, so what I did, yeah, so in this picture here, so like. Here, so if I look at like. What do I want to say? Sorry, just 1 second. So this blue thing I've outlined in this base, this B unit base, I've written as the base for the mirror to this guy. And so what this guy here, let me like again, maybe try and use the board to do some like, well, maybe not. So this guy, by this guy here, I mean like I've taken, so this is my cartoon figure where I've taken like P1 times P1 and then blown up. So these red things record like blow-ups. So this P1 times P1, and I've blown up like twice of these two sides here, and then 2 blow-ups there and there. So then I would imagine that the mirror to that guy, so the mirror to this blow up of P1 times P1, fibers above this blue region here.
Okay.
But then you can see that all such mirrors are going to include, like, no matter how many blow-ups and how many rays or how many depth divisors I do, I can include that into such a mirror story like so. So that help?
I'm gonna scroll up to the picture for that. Okay.
Right. So then
I guess it doesn't look exactly like the cross dot that you had. I don't know if that was a thing, but
I guess what I've done in that, right? So just give me a second to figure out how to best use the board / screen combination here. So maybe I can still write and then like. So I think it has something like this. So what I've done is I've sort of omitted, so previously I had these rays, but these rays are just telling me, so I haven't drawn the rays in this picture here, You're right, but the rays are telling me the monodromy of your integral affine stretch. So I have this lambda here is some bundle sitting inside of like the cotangent bundle. I can read off the monodromy, like I can build this, I can build such a bundle that I specify the monodromy, and the monodromy is going to be shearing along the direction specified by the rays. So the point is that like I have this lattice bundle and the cotangent bundle of this B unit, and the monodromy of that lattice bundle around each of these points here, I can read off by this like slit coming off of it. And the point is that you shear in the orthogonal direction to that slit. So now let me just move on. So now I can show you why this was a nice sort of representative or like generators of the spheres of E that I could pick. So SL2Z acts on, so I wanted to find some action of SL2Z and E on my like universal mirror space in unit. And so I can define the action of SL2Z because this B unit that I drew, so recall that B unit just had like a singular fiber above every point in Z2 minus the origin with sort of monodromy specified by the ray that point led on. So that space, you can act on that base by SL2Z, and then that's going to induce an action on the entire federation in unit. So here again, these color coding would be more useful if the screen was bigger. But you can imagine, I think here, what I've tried to do, I think I've successfully done it, is sort of rotated clockwise by 90 degrees. And that would correspond to this 0, -1, 1, 0 element and SL2Z, or I think I deleted on the board, but this is just the element that's in like X, Y to Y, X inverse or something like that. But now we have the tricky one is actually this E. So E is going to act by this nodal slide and cut transfer business. So what's happening is that I can form some family of like, so given one of these diagrams, these like split diagrams like this, I get some symplectic Bohr manifold over it. That's sort of the beauty of these split diagrams. And I can form a family of symplectomorphic manifolds by what I do is I like take, let me like, yes, great. So I can, I flew too close to the sun. No. How do I do it? Oh yeah, this is the stuff I'm not going to talk about. No, now my slides are like all okay. Okay, great. No, okay, gotcha. Great. So let me try to do this without. Okay, so if I start sliding this slit down here, and I slide him all the way, and I sort of slide everyone on this ray, on this vertical ray, down, so that they all sort of line up. So you move them all sort of down along this ray, and then. So that's the so-called nodal slide. That's a family of symplectomorphic manifolds. And then there's sort of nothing special about the direction of this cut. So I could now say, well, I'm going to draw the cartoon of this space by having the cut go the other direction. This is the so-called like cut transfer. And I end up with a new symplectic manifold. That new symplectic manifold is manifestly identical to the one I started with. So by taking this sort of family of symplectomorphisms, and taking me to a new space and saying, oh, well, this new space I can identify with my original space. It's because it's manifestly equal, I get this symplectomorphism E. But what's happening here geometrically is like away from this, like some small neighborhood of the pre-image of this ray in my M universal. On the right-hand side, I'm just acting by the identity. So my symplectomorphism isn't doing anything on sort of like 1/2 of the space, but on the left-hand side, I'm acting by a shear. So I'm pushing all of the singular fibers around by this shearing motion, and this is my symplectomorphism that is going to be near to my map E. And so the reason I chose E as my generator is because this nodal slide and cut transfer move is sort of one of your elementary transformations you can do on these integral affine bases. And so it's nice that move has a nice description in terms of the cluster transformations on the original variety. So that's how I define the mirror of my generators. And then now I've like completely lost control of the screen. Well, let me pause there for questions before I think the punchline here is something like if you're giving this talk to a bunch of low-dimensional topologists or four-manifold people or something, it's like, well, I can actually use this birational transformation group to get out some interesting symplectomorphisms of four manifolds. For me, for my taste, I don't actually think that that's what I think this is actually cooler for is it lets you see some geometry of this birational transformation group very easily on these four manifolds, like from the mirror. So let me show you like an example of what I'm talking about. So if you look at the Markov cubic, so this Markov cubic, so again, this is one of these little cartoons, but what I've done to get this Markov cubic, so I've taken P2 and I've blown up the interior point of each of the toric boundary components twice. So I have my original triangle of lines, and now I have two lines sort of hanging off each of the original components. Then you can say, okay, and now I look at the interior of that. So in the interior of that, there's this large group of automorphisms sitting inside of, there's this large group sitting inside of the automorphisms of the interior. So the free product is Z-mod 2 with itself 3 times. What are the generators of this group? It's easy to see generators if you embed Y into P3 as a, well, you map Y into P3 as a degree 3 surface. This is almost an embedding. So then you can ask, if I look at a line intersecting the image of my Y, well, that it's a degree 3 surface, so the line is going to intersect the image of that Y in 3 points. So I define these reflections about each of the vertices of my toric boundary divisor. So I say, okay, well, I'm going to send a point in my surface, in my interior of my surface, to the other point, which is collinear. Sorry, if I like this R sub X is going to be a reflection about X, so I send Y to the point that's collinear with Y and X, and then similarly I can have Y sub R sub Y and X sub Z. What do I want to say about that? Okay, so if I think about what's happening here, that's type of, so we should say E. So if I factor this, this reflection here, in terms of my generators for my Beer sub E group, it factors as this should say E squared twice here, and then this map. So now you're going to tell me that this is not actually an SL2Z. I agree with you. It flips the sign in volume form 1 0 0 1. So I can read out from this cartoon. So this cartoon is like fairly literal for the 4 manifold. So like so the mirror to this Markov cubic is going to be some almost toric vibration that has 6 singular fibers, like so. And then I can do this nodal sliding cut transfer twice. So that what that does is it sends these 2 points, these 2 singular fibers down. And this whole side gets sheared sort of twice. So this ray goes up to here. And then now I just flip everything about the x-axis there. What I note is that in order to do this, this move, I can do this nodal sliding cut transfer if I like have another ray I can slide down towards. So in order to resolve the singularities of this these maps, I had to blow up the interior here. So the point is that these generators do not extend to an automorphism of your YD. What they do, in order to resolve them, you have to blow up the original Y. In general, you get these like tree of blowups of your original cubic surface that let you resolve like the elements of this Z-mod 2 free product itself 3 times. You can read off the blowups you have to do from these sort of the sketches here, which are also like acting honestly on the board. So let me stop there. I tried to end on the actual.
Sure.
I think that ended that.
Oh, no,
No, yeah, please.
No,
Yeah, I think-
Well,
We started, it's on your call, of course. but
Yeah, you
we
started
started-
in here because I think that the second chapter of this is it's very confusing very fast. So let me just
Oh,
Yeah.
okay.
yeah.
I guess. Yeah, maybe it's more clear if I like knew more about these those MWs, but like
Mhm.
why they had this really cool picture, fibered over B.
Yeah.
Like is that just kind of something you expect from I guess
So
Yeah,
it's a
like-
question of
like-
what I expect is like
Yeah.
to have some.
well, it looks like the W's or the M's are also like have this sort of fiber type thing going on, but I mean
Right, so the M's have this Lagrangian force vibration.
Okay.
And it's a good question. So indeed, you expect the mirror symmetry correspondence to be because of some SYZ mirror symmetry, which may be what you're hinting at. Like you
Okay.
you see some Lagrangian perturbation on the interiors of your YD as well, and indeed they are dual Lagrangian perturbations. And that is a story. Yeah, that I did not have time to get into, but you expect you expect to build these guys out of these almost vibrations because of some like SYG principles.
Okay.
Yeah. Again, the general principle of like how much mirror you can if you have like a pair of mirror spaces, then often they have some discrete dual Lagrangian vibrations. Let me say that like that's not actually how Paul and Elsa, when they built their mirror to these YDs, they built it as a electric vibration, like they built it with the superpotential W, which like you guys might have noticed that like I didn't really use that superpotential at all. It's the story with the description in terms of the almost vibrations is somewhat parallel, but it's the correct one to get to see like it's the correct one for these purposes because well, because it works, right? Because I can actually write down what these generators do in terms of the almost vibration very easily. If I try to write down what these generators did in terms of like I could have done this whole story with these left shift vibrations and like these W superpotentials, and I had some like system of left shift vibrations. And you could do it that way, and that's actually what Elsa and I tried to do at the beginning, but it gets super messy, like super fast, and it's actually much cleaner to just work with the almost vibration picture. You need some comparison to go between well, this is more of a technical point, but you need some comparison to go between like the Fukai and Battle categories that they work with for the mirrors, and some Fukai Saito categories which are more adapted to the almost vibration pictures. And that is and that's a part of the story I don't really want to get into, but that's sort of yeah.
What will be a summary of the next chapter of this?
Yeah. So let me see. So the next chapter is like, what about the full group? And so if you want to think about the full group, well now you need to step away from just considering these log logarithms with their distinguished complex structures, essentially because you're going to have to be able to blow up any point you want in the toric boundary dividers, not just like these distinguished points. And so then, if you want to do that, you're going to have to consider, well, you're going to have to consider the set of all log logarithm services with, like, you're going to have a much bigger set of services you have to find the mirror to, and on the mirror side, what that's going to correspond to is deforming the symplectic form. So I didn't say this, but all the symplectic manifolds I constructed were exact. But in general, in order to see the deformations on the complex side, see the mirror on the A side, the symplectic side, you're going to have to start deforming your symplectic form. And so you end up with what you should imagine is like some family of symplectic forms on that M universal, or family of complexified Taylor forms on that M universal. And it's some huge family, like it's some family over essentially your deformation space is something like every single possible point I can blow up gives me some sort of deformation. So it really deforms. It's infinite dimensional, and it's like C to the D2 minus 0. And I'm just saying that because it's like that's corresponding to the like set of all interior blow code. So you would have to figure out how to put the symplectic form. So you have to figure out how to put like some kind of symplectic forms on that. But then what you do is you end up with some mirror systems of families. So that's what so yeah, so what this corresponds to in these pictures of the universal is like previously all of my slits were sort of lined up, but now I'm going to deform. So it's actually easy to see the symplectic deformations. I just like push the slit, the singular fibers sort of off their parallel slits in a way that it's very explicit. Like you push your slit off of the ray by amount, which is just equal to like the log norm of the amount, the log norm of the point that you're blowing up in the interior divisor. So it's not so bad. And then what you would do is you want to say, let's see if I can actually, then you have to figure out there's a bunch of sort of annoying technical points. But you would end up with some map from this birational transformation group to this simp underline group. So this simp underline group means that it's a family of symplectomorphisms. You should imagine that this M universal has a family of symplectic forms, and I have a family of symplectomorphisms matching up like the fibers of this family with itself again. I mean, it's a bigger thing. And then so that's conjecture 2, is that there is such a map. This is conjecture 1. This conjecture 1 here, or conjecture 2 here, says that everything acts like as you'd expect. So once you actually restrict to one fiber of your family, and then you restrict to the subdomains, that you get an honest symplectomorphism of non-exact mirrors compatible with HMS. And if you assume that you found the correct mirrors, which is harder, so this is sort of work in progress with me and Andrew Canlon maybe, or other people. I mean, I don't know, whoever gets their first wins. But if you assume HMS with families, then all you need to do is a little bit of technical, a little bit of analysis, and you would say, okay, this is actually the story. So, but the statements are sort of less nice, I guess.
Can you say again? You said the motivation is not so much to produce nice and interesting symplectomorphisms on the mirror side, but
I think it depends on you as motivation. Like I think if you have motivation. I think. Well, okay. Let me say something that I think some people's motivation would be. Like I think, for example, Elsa, like my collaborator, is very interested in sort of describing these symplectomorphisms. Like I think, you know, it's these symplectomorphism groups of four envelopes. There's not very much known about them. It's not known, for example, what the symplectic mapping class group of a lot of spaces are.
Sorry about what
it's not known what like the symplectic like these symplectomorphism groups of four manifolds are like not that well understood. So it's cool to be able. It's nice to be able to produce them. I think for me, in general, I like. You know, whenever you're doing homological mirror symmetry, I think there's a little bit of interplay of like how you want to pass information between. For me, I think it's a little bit cool to say, well, I can actually draw these little pictures of like morphisms of four manifolds, and then maybe that tells me interesting things to look for on the B side. So, or you could just say, okay, well, here's an interesting group, like this fearsome E group, and like here's some interesting things it acts on, and voila. So.
When you say not much is known, I mean, to what extent are diffeomorphisms better understood as symplectomorphism groups? I mean, so it's not known that some diffeomorphisms which are known to be simple, but you're saying, for example, that's not known for symplectomorphism.
That's right. That's right. Yeah. Yeah.
Okay.
And I mean, it's also not clear. So for some spaces, I think you expect that like the symplectomorphism groups are actually equal to like mapping class groups, maybe. Like any like sort of for like a simple space, like I think if you look at like maybe sorry, I don't know the theorem, but I don't think very much of it.
Questions? Think Abigail again.
Thanks very much for your thinking.
I don't think you. Yeah.
Sorry, I think the timing was slightly off. I was trying to adjust things on that clock.
Oh, yeah.
But
That's not good. Yeah.